This is the 7th video in a series covering abstract linear algebra. In the previous video, we looked at the notion of a vector space over a field K, as well as several examples of vector spaces over an arbitrary field K, as well as specific fields like the real numbers, or the complex numbers, or even finite fields Fp. So today we want to look at a natural substructure of a vector space called a subspace. So let's look at the definition. So let's suppose that V is a vector space over a field K and W is a subset of V. So at the moment, it's just a subset, no other structure. We say that W is a subspace of V if it has the following two characteristics. So first off, W with addition is a subgroup of the abelian additive group V with addition. Let's just recall what that entails. That means the zero vector is in W. That's the additive inverse of the vector space V. If V and W are in W, they're vectors in W, then their sum is in W. So that means W is closed under this addition operation. And then furthermore, if little w is in W, then minus little w is in W. So it's closed under taking inverses. So all of these three things here are all wrapped up in this word is a subgroup of. And then we have one more condition having to do with our scalar multiplication. And that is if W is in W and alpha is in K, then alpha W is in W. So in other words, W is closed under scalar multiplication. So if you recall, when we looked at subgroups, we had something called the subgroup test, which simplified the process of checking if something was a subgroup. Well, we've got something similar for vector subspaces, and that's called the subspace test. And that says that W is a subspace of V if and only if for all alpha in K, V and W in W, we have alpha V and V plus W are elements of W. So in other words, all we need is closure under scalar multiplication and vector addition, and we get all of the rest of these for free. So notice the vector addition and the scalar multiplication are only two of the four things that you would really need to check to show something is a subspace. So this maybe halves the number of things that you have to check. Okay, so this is an if and only if statement, which means there's a forward direction and a reverse direction. Let's notice that the forward direction follows very, very quickly. That's because these two statements right here are contained in the definition of a subspace. So let's focus on the reverse direction. So like I said before, we know this condition is true and this condition is true. That's because we are assuming the right-hand side of this if and only if statement. So all we really need to check now is that it's closed under additive inverses of the vector space and contains the zero vector. Okay, so let's maybe first show that it contains the zero vector. So let's take any W in W, and then note that the number 0 in K has the following property. So 0 scalar multiplied into W gives us the zero vector. But because of this closure rule, we know that that is in W. So in fact, we know the zero vector is in W. And from time to time, I'll distinguish the zero vector from the zero scalar with an arrow. And I should maybe point out over here, we mean the zero vector. Okay, good. So that's this property taken care of. Now we need this property. And that's going to be just as quick. So maybe let's also notice that -1 times W is equal to -W by something that we saw last time. But again, this is a scalar multiple of W by an element from K. -1 is in K. That means by the property up there, this is an element from W, which means this is an element from W. So we get that minus W is an element from W. And that's really all there is to it. But it was important to check these two things because as we look at examples of subspaces, it's a lot quicker to check these two properties than it would be to check all of these properties over here. Okay, so let's get rid of this, and then we're going to go through a bunch of examples. So now that we've explored the definition of a subspace, we're ready to look at a bunch of examples. So the first several examples we'll look at will be subspaces of a vector space K2, where K is any field. Let's recall that that's going to be all vectors that have two components like this. And as we discussed last time, we could write these as a column or as ordered pairs. We're going to choose to write them as a column because that'll be more helpful later. So just to reiterate, we defined this kind of thing last time, so we know how the addition and scalar multiplication works on this type of object. Okay, so let's start with our first subspace. So I'll say W is equal to the following set. Let's say x0, where x comes from K. So in other words, the first component can be anything we want, and the second component has to be the number 0. So let's check this as a subspace. Recall, all we need to do is check that it's closed under vector addition and scalar multiplication. So let's suppose V and W are in W, and then alpha is from K. But the fact that V and W are in W tells us that they have the following form. V is of the form x0, and W is of the form y0, where x and y are in K. Okay, so now let's add these two. So notice we've got V plus W will be exactly x plus y 0, but that most definitely has this form, because if we add two elements from the field, we end up with an element from the field. Then if we add 0, we still get 0 up here. So recall the condition is that we have the second component is 0, and we have maintained that. So this is most definitely in W. And then we can also check maybe alpha times W will be equal to alpha y 0, because anything times 0 is 0, so alpha times 0 is 0. But that's in W as well because it has this shape. So this fact right here and this fact right here check that this is definitely a subspace. Okay, let's look at another example. So our next example is really important, and it's also a subspace of this K2. So here our vectors will be of the form x1, x2, but instead of these being free, they satisfy the following linear condition. And this linear condition is a times x1 plus b times x2 equals 0. And here a and b are just some numbers from the field K. Well, they're fixed, but they're from the field K. Okay, good. So let's check that this is a subspace. We need to check that it's closed under addition and scalar multiplication. So let's take V and W in W, and then we'll take alpha in K like we just did. But this means that we can set V equal to x1, x2 with ax1 plus bx2 equals 0. That's the entry fee to be inside of W, is that when you add the components together like this, you get 0. And then W will be equal to y1, y2, where a y1 plus b y2 equals 0. Again, that's the entry fee into W, is that when you add the components together, you get 0 like this. Okay, so now let's notice that V plus W, but now adding these component-wise, I get x1 plus y1 and x2 plus y2. And now our goal is to check that this is in W. So how do we check that it's in W? Well, it must satisfy this linear equation where the role of x1 is being played now by x1 plus y1, and the role of x2 is now being played by x2 plus y2. Okay, so let's check that it works. So we need to look at a x1 plus y1 plus b x2 plus y2. Hopefully we get 0 for that. If we get 0 for that, then our sum is definitely in W. But now I can quickly rewrite this so it's pretty clear. And I can quickly rewrite this as a x1 plus b x1 plus a y1 plus b y2. Sorry, this should have been an x2 attached to the b. But again, given the fact that v is in w, we know this is 0. And since w is in w, this is 0. So this turns out to be 0 plus 0, which is equal to 0. So the fact that we got this tells us this is indeed in w. And I'll let you guys check the scalar multiplication. The idea is exactly the same. Okay, so I want to look at a special case of this example when k is the real numbers. Okay, a very special case of this last example is when v is r2 and w is x1, x2, where x1 and x2 satisfy the following equation. So 2x1 minus x2 is equal to 0. Okay, so let's recall that we can take this equation and we can solve it for x2. So let's note if v, which is x1, x2, is in w, then 2x1 equals x2, which means we could really write v as, let's see, maybe x1, 2x1. In other words, x1 times 1, 2. So in other words, v is a scalar multiple of the vector 1, 2. Okay, but if we go down here and draw the Cartesian coordinate plane, which is a good analog for R2, notice the vector 1, 2 can be written like this. So it's 1 unit along the horizontal axis, 2 units along the vertical axis. So it looks something like this. This would be our vector 1, 2. And then if we take any scalar multiple of this vector, as we discussed in a previous video, that just builds this entire line. So that's what we're doing here by letting x1 be anything we want, is we're building this entire line. So a nice picture for this vector space or this vector subspace W would be this line. So let's maybe get rid of this and we'll look at some more examples. So for our next example, we'll fix the field as the real numbers, and then we'll look at a family of vector spaces C in R, which are all n times differentiable functions from R to R. So these are all vector spaces on their own, because if you add two n times differentiable functions, you get another n times differentiable function. And that's because of the sum rule for taking the derivative. Okay, furthermore, we know that if we start with C0, which is all continuous functions, well, we know every differentiable function is a continuous function. And generally, what we say is a differentiable function would be a 1 times differentiable function. So like I said, every differentiable function is a continuous function. So we have a subspace relationship between the continuous functions and the differentiable functions. And now we can keep going to the right. So C2R will be a subspace of C1R, which is a subspace of C0R. And then C3R, so that would be all 3 times differentiable functions, is a subspace of C2, which is a subspace of C1, which is a subspace of C0. And we can extend this all the way back. And there's actually a guy that's at the very end of it called C infinity R. And that would be all functions that can be differentiated infinitely many times. So I think this is a nice picture of a nice string of subspaces based off of this very important vector space, which is the vector space of continuous functions. Okay, so let's look at another example. So this example is going to look a lot like the last one. So let's start with the vector space of all polynomials with coefficients in k. We saw that that was a vector space in the last video. And now let's define k sub n of x to be all polynomials of degree less than or equal to n. And just while we're at it, let's point out that the degree of the number 0 will be defined as minus infinity. Okay, so let's look at some examples here. So we have k1x. Well, that's going to be all degree 1 polynomials, or everything that's of degree 1 or less. So that'll be stuff like this. Maybe we'll write it as a0 plus a1x, where a0 and a1 are free to come from k. So that would be an example of k1x. And then k2x, would be a0 plus a1x plus a2x squared. And here a0, a1, a2 are in K. So I think that gives you a good idea of what's going on here. So you might look at this and say, well, why do we need degree less than or equal to, and why not the degree equal to n? And that's because that is not closed under addition. And we can check that pretty easily. Notice that we would have x squared plus 3x is of degree 2. But if we add that to negative x squared plus 5, we end up with 3x plus 5, which is degree 1. So we ended up with the sum of two degree 2 polynomials being a degree 1 polynomial. Furthermore, if all of the polynomials are of degree equal to n, then it will not include the 0 polynomial, which we said had degree minus infinity. So I'll let you guys check that this is closed under the vector addition and the scalar multiplication. That's pretty easy to do. But now let's notice we've got a situation that's pretty similar to what we had on the last board, where just the inclusions are reversed. So over here on the left, we have K, which is like all 0 degree polynomials, just the ground field. We talked about why that was a vector space last time. That's going to be a subspace of K1 adjoin X, but that's going to be a subspace of K2 adjoin X, which is the subspace of K3 adjoin X, so on and so forth. And that's because, recall, K3 is all the polynomials of degree less than or equal to 3. That includes polynomials of degree 2 and less. And that's going to go on and on and on. But then there's going to be a certain space that is kind of above all of this. And that would be the vector space of all polynomials. So this is some sort of limiting object. Okay, so let's get rid of this and we're going to look at just one or two more examples. So now I've got two more quick examples, and these are going to be subspaces of differentiable functions. So as sets, I've called them W and W prime. So W will be all functions. When we evaluate them at 3, we get 0. And then W prime will be all functions so that when we take their derivative, we get themselves. So let's check that each of these are subspaces. So let's maybe color code this one orange, and we'll do this first. So let's suppose that F and G are in W. Remember, elements from W are elements from C1R with a condition, so they are functions. And then we'll take alpha, which is a real number. We need two vectors, which are functions in this case, and we need a scalar, which is a number in this case. And so let's notice, because F and G are in W, we know that F of 3 is equal to 0 and G of 3 is equal to 0. That's the entry fee to get into W. You have to evaluate at 3 to 0. So now let's look at F plus G evaluated at 3, but that's exactly F of 3 plus G of 3, which is equal to 0 plus 0. But 0 plus 0 is equal to 0. But if we evaluate F plus G at 3 and get 0, that means that F plus G is in W. That means that W is closed under our vector addition, which is addition of functions here. Now let's check alpha F evaluated at 3, but that's going to be equal to alpha times F of 3, which is alpha times 0, which is 0. But that tells us that alpha F is also in W. So in other words, W is closed not only under the addition, but scalar multiplication, meaning that it is indeed a subspace. So let's move on to this next one, this red dot, and see if we can do the same thing. So let's suppose that F and G are in W prime, and then alpha is in R. So let's notice that since F and G are in W prime, we know F prime of X equals F of X, and G prime of X equals G of X. That's the entry fee to be in W prime. You are your derivative. But now let's take F plus G prime of X, and notice by the sum rule for the derivative, we get this as F prime of X plus G prime of X, but then that's going to be equal to F of X plus G of X. because it was given that f and g are in W, but that's exactly equal to f plus g of x. But that's exactly what we need for f plus g to be in W prime. So that means W prime is closed under this vector addition, which is addition of functions. Okay, and I'll let you guys check that it's closed into the scalar multiplication. The strategy is essentially the same. So I'm gonna get rid of this, and then maybe I'll tweak each of these so that they are not subspaces. We'll check, and we'll describe very quickly why they are not subspaces. So I've quickly tweaked my last example so I have things that are not subspaces. Now let's see how we can show they are not subspaces. And often you can do it the easiest way possible. So now W is defined to be the set of all functions f that evaluate at 3 to the number 1. But let's notice that the 0 function is not in W. So we're reading this as the 0 function, and that's because the 0 function evaluated at 3 is equal to 0, which is not equal to 1. So the 0 function is not in W, but that's one of the things that we need in order for W to be a subspace. Let's also check that it's not closed under scalar multiplication. And we can do this via a counterexample just like we did here. So let's take f in W, and then we'll look at what happens when we do scalar multiplication, say by 2. So let's answer the question, is 2 times f in W? Well, the answer to that is no, because 2 times f evaluated at 3 is equal to 2, which is not equal to 1. And again, the entry fee to be inside of W is you have to evaluate to 1. This does not evaluate to 1. You can also very easily check that if you take the sum of two things in W, you still don't get something in W. Again, because 1 plus 1 is equal to 2, it's not equal to 1. Now the same thing goes right here. Maybe I won't check this one. I'll leave this one as part of the warm-up exercise, is to check that this is no longer a vector space if we change the condition to f prime equals f plus 2. Okay, nice. Okay, so let's get rid of this and we're gonna look at a couple more definitions. So we'll finish this video off with the notion of a linear combination and the span of a set of vectors. So let's suppose that V is a vector space over a field K, and alpha 1, alpha 2 up to alpha n are elements from K. So in other words, they are scalars, and V1, V2 up to Vn are elements from V, so they are vectors. Then the linear combination of V1 up to Vn with weights alpha 1 up to alpha n is the following sum. So it's alpha 1 V1 plus alpha 2 V2 all the way up to alpha n plus Vn. And then it's also important to wrap all of these linear combinations into a set all their own, and that set is called the span of these vectors V1 to Vn. More precisely, the set of all such linear combinations can be written like this. So we've got span of V1 up to Vn. That's going to be the set of all things that are of the form alpha 1 V1 plus all the way up to alpha n Vn as alpha I. In other words, alpha 1 up to alpha n ranges over all values from the field K. So this is a single vector because in this definition we have fixed the alphas, whereas this has potentially infinitely many vectors. Actually only finitely many vectors if we're dealing with a finite field here. And that's because these alpha I are ranging over all elements from K. So the best way to think about a span is really like as a subspace generator. So it takes a set of vectors and it generates a subspace out of those set of vectors. And in fact, that's what we'll prove in this proposition, which will be the last thing that we prove here, that the span of V1 up to Vn is indeed a subspace of V. So let's see how this proof goes. So let's introduce some notation. So let's set W equal to the span of V1 up to Vn, and then we need to take two vectors from W and a scalar and show that this set is closed under the vector addition and the scalar multiplication. So let's take maybe we'll call them V and W, not subscripted, from W, and then we'll take alpha from K. But now since V and W are in this span, and the span is all vectors of this form, we can write down a general shape for V and W. So in fact, we can write V equals alpha 1 V1 plus up to alpha n Vn, and then W is equal to beta 1 V1 plus up to beta n Vn. And here the alpha I and the beta I are from our field, so K. And now let's look at V plus W. So V plus W will be equal to, well, I'm going to write it like this, alpha 1 plus beta 1 V1. So it's like I'm combining like terms, plus up to alpha n plus beta n Vn. But look at this. This is exactly the type of shape that we need in order to be within the span. And that's because since alpha I and beta I are in K, their sum is in K. So all of these little things are in K here. So we have another linear combination. So this is in W. Now let's check that it's closed under scalar multiplication as well. So we'll do alpha times V, but just doing the distributive rule, that will give us alpha 1 times V1 plus alpha n times Vn, where we've actually used not only the distributive rule, but the associativity of scalar multiplication with the multiplication in the field to rewrite it like this. But that has the shape that we need, again, because all of these products are in K. So this is indeed a linear combination of our vectors, which makes this object also in W. These two things together tell us that we do indeed have a subspace, and that finishes this proof. Okay, so let's get rid of this and I'll leave you with some warm-up exercises. So I've got a couple of warm-up exercises. The first is a generalization of one of our first examples of a subspace, and that is the following subset of Kn. In other words, these n-component objects. So we've got x1 up to xn, where xi comes from a field K, and they satisfy the following equation. So a1 x1 plus a2 x2 all the way up to an xn is equal to 0, where those ai's are fixed. So you want to show that is a subspace of Kn. And for our next one, instead of having a single equation, we have two equations, and we're looking at the special case of R3. So here we've got x1, x2, x3, where x1 minus 2x2 is 0, and x3 minus 3x2 is 0. So work through all of the steps showing that's a subspace, and then describe it geometrically. Then finally decide if the following subset is a subspace of R2. So we've got x1, x2, where x1 plus x2 is equal to 9. And then repeat this for F3, 2. So in other words, the ground field for this last example is the field of 3 elements. And then describe the geometry in that last example. Okay, so to reiterate, do this 2 different times, one viewing it with real numbers and one viewing it with these integers modulo 3. And that's a good place to stop.